So we're slowly winding down our work with systems of differential equations. So we're going to spend a couple of days talking about non-homogeneous systems.
I just don't own purple. Like, I feel like you'd be weirder if I did.
So today we're going to talk about undetermined coefficients. Oh, and just so we all are on the same page, quiz on Monday. Quiz on Monday only goes through section 8.2, so solving systems 8.1 and 8.2. There are 4 questions that have to do with kind of the theory of systems, and then 4 questions that ask you to solve systems. So, with higher order differential equations, we saw that under certain conditions we can use undetermined coefficients to solve our non-homogeneous equation. The process is exactly analogous for systems, but just up front I'm going to say the method is a little more limited. And there are many more requirements in terms of how we use undetermined coefficients, especially when our complementary solution contains the same functions as the function in that we're looking for our particular solution for. So just be aware of that ahead of time. We have the same requirements for f of t. So the equations or the functions that make our system non-homogeneous. So we must be, just a reminder, they have to be polynomials. Exponential functions. Trig functions, or products of these. Just like before. And we pick our functions for our particular solution, the form of our particular solution, in the exact same way. We look at the form of f of t, and we pick the form of our particular solution. So I just want to go through a couple of examples using undetermined coefficients. So x prime, 5, 9, negative 1, 11, x plus 2, 6. So this 2, 6 vector makes our system non-homogeneous. This is probably the most desirable form of our y sub p with constants here. So as before, we need to find x sub c first. So we solve a minus lambda I equals 0. So 5 minus lambda, 9, negative 1. 11 minus lambda. Hopefully this is familiar by now. This gives us 5 minus lambda, 11 minus lambda, minus 9 equals 0, which becomes lambda squared minus 16 lambda plus 64 equals 0. Plus 9, yes. And this gives us y minus 8 squared equals 0. So we have a repeated eigenvalue of lambda or sorry, not y, lambda, upside down y. Lambda minus 8 squared. So we get a repeated eigenvalue of lambda equals 8. So we need to find our eigenvectors. So for lambda equals 8, we get, when we substitute in here, we get negative 3 k1 plus 9 k2 equals 0, and minus k1 plus 3 k2 equals 0. Those are both the same equation. That's 3 k2 equals k1. And I let k2 equal 1, so k1 equals 3. So our eigenvector is 3, 1. Now we need to solve a minus lambda I times p equals k for p. Found k here. So when we substitute in here, we get our same system. These k's become p's, and the zeros become 3, 1. So we get minus 3p1 plus 9p2 equals 3, and negative p1 plus 3p2 equals 1. And I just looked at this last equation because the numbers are smaller, and I just said let p2 equal 0 and p1 equal negative 1. And that would also satisfy that first equation as well. So we get p is negative 1, 0. So x sub c, our complementary solution, c1, 3, 1 e to the 8t plus c2 times 3, 1 t e to the 8t plus negative 1, 0 e to the 8t. All right, so we have that part done. I'm going to switch pages instead of keep scrolling down. So because our constant, because this vector is constant, we're just going to assume that y sub p is a constant. I should say x sub p. Is just a constant vector a1, b1. And we're going to substitute this into the original differential equation. So we're going to substitute that into x prime equals ax. And when we do that, this is nice because the derivative of a constant is 0. We get 0 equals 5a1 plus 9b1 plus 2. So I'm substituting in here 5a1 plus 9b1 plus 2. And we get 0 equals negative 1 a1 plus 11 b1 plus 6. So zeros from the derivatives, this from multiplying by the matrix A, and this is our function here. Our function would happen to be a constant. So we have a system of equations, 2 variables, 2 equations, 2 variables. So we can use substitution, we can use elimination. I think I added or multiplied this by 5 and added.
I think we should use the squiggly lines.
Yeah, I like the squiggly line. So, and I'm going to say just because of what's written on the board back there. Row operations. Actually I use substitution, but we can say we use row operations. And we get A1 is 1/2, and B1 is -1/2. But this system's not a difficult one to solve. So our particular solution, x of p, in this case is 1/2, -1/2. And our general solution is going to be C1, 3(1) e to the 8t, plus C2, t e to the 8t, plus -1, 0, e to the 8t, plus 1/2, -1/2. So not terrible. That process is not terrible. All right, let's look at one more example with a little more complicated but still pretty simple functions. Any questions there? And again, we're using undetermined coefficients, involves more systems of equations, more than we used just to solve the equation. X prime, -1, 5, -1, 1, x plus sine t, -2 cosine t. So trig functions, not terrible. We know from higher order differential equations when we have trig functions, undetermined coefficients usually turns out not too bad. So we want to solve the homogeneous system first. We want to find the complementary solution. We're going to do our normal procedure, solve a minus lambda I, determinant is 0, which is -1 minus lambda 5, -1, 1 minus lambda. That determinant is 0. So -1 minus lambda, 1 minus lambda plus 5 equals 0. This gives us lambda squared plus 4 equals 0. So lambda equals plus or minus I. 2i, sorry. So we have complex eigenvalues here. So we'll use our process for our complex eigenvalues that we talked about yesterday. So for lambda equals 2i, we get our equation that we're going to solve is -1 minus 2i k1 plus 5 k2 equals 0, and negative k1 plus 1 minus 2i k2 equals 0. I use the second equation. This becomes k1 equals 1 minus 2i k2. So I said k2 equals 1, and k1 is 1 minus 2i. So our eigenvector is 1 minus 2i 1, which we can separate into real and imaginary parts. And I thought about the question you asked yesterday, Max.
Mm-hmm.
about this one. If we had picked a complex value for K2, then K1 would also, so both of them would be complex, and this would not be 0. So if you didn't pick nice simple numbers, or less nice, less simple numbers, you could get this value not to be 0.
Is there any reason you might do that?
I would say no.
Okay.
Pick the easiest numbers. That's always my goal, is to pick the easiest numbers. So our real part is this vector 1, 1. The imaginary part is vector -2, 0. So our solution, our complementary solution, x sub c is c1 times 1, 1 cosine 2t minus -2, 0 sine 2t plus c2 -2, 0 cosine 2t plus 1, 1 sine 2t, which we can write as c1 and c2 -2 cosine 2t plus sine 2t, and this is a sine 2t in this row. There we go. There's our complementary solution. Now we're going to find our particular solution. So I'm going to change pages here. So we're going to say that x sub p is some constant a1, constant vector a1, b1 times sine t plus another constant vector a2, b2 times cosine t. Just like we would pick for a higher order differential equation when we were using undetermined coefficients, a sine t plus b cosine t. But we need vectors here because we have a 2 by 2 system. So we need to substitute this into the original system. So we need the derivative. So x of p prime is a1, b1 cosine t plus, and I'm going to write that since this gives us a negative, negative a2, negative b2 cosine t, or sorry, sine t, when we take the derivative. So our derivative, a1, b1 cosine t plus negative, I'm gonna write it like this. I'm gonna write it in rows rather than as matrices. So we get a1 cosine t minus a2 sine t, and when we multiply this sum by our original matrix and add sine t and negative 2 cosine t, what I get is negative a1 plus 5b1 times sine t plus negative a2 plus 5b2 cosine t plus sine t. And for my second row, I get b1 cosine t minus b2 sine t equals negative a1 plus b1 sine t plus negative a2 plus b2 cosine t minus 2 cosine t. And again, this is coming from multiplying this. We could write this out as a1 sine t, b1 sine t, a2 cosine t, b2 cosine t. Multiplying that by this matrix, and then adding the sine t and the negative 2 cosine t. So now we need to equate coefficients. And I'm going to combine some things and have the right-hand side be 0. So when I combine my sine terms and my cosine terms here, I get a1 plus a2 minus 5b2 cosine t plus a1 minus a2 minus 5b1 minus 1 sine t equals 0. And here I have a2 plus b1 minus b2 plus 2 cosine t plus a1 minus b1 minus b2 sine t equals 0. So what we need in order for these equations both to equal 0 for all values of t, we need a1 plus a2 minus 5 b2 to be 0. We need a1 minus a2 minus 5b1 minus 1 to be 0. We need a2 plus b1 minus b2 plus 2 equals 0. And we need a1 minus b1 minus b2 equals 0. So for our function of a sine and a cosine in a pretty simple system here, we end up with 4 equations with 4 variables that we're solving.
That's a squiggly line on the flat.
That's definitely a squiggly line. I tried for a while to find a clever way to solve this by combining some things and doing, and I couldn't figure out a clever way to solve this. So it was down to row operations, and I'm going to say slash technology. We get a1 is negative 1/3, a2 is negative 3, b1 is 1/3, and b2 is negative 2/3. The most difficult thing with using technology is making sure you get this typed in correctly. You miss a sign and your answer comes out wrong. But this, I wanted to do this example to point out for a relatively simple system, relatively simple functions, we're down to a 4x4 system of equations that we're solving. So that's, again, not difficult, but it's a lot of work. So our particular solution, finally, is negative 1/3, 1/3 sine t plus negative 3, negative 2/3 cosine t. And our general solution takes almost as long to write this as it does to do the whole problem. And there's our solution.
What does this mean? Like, it's just a bunch of sines and cosines. Like, what does that look like?
So this is telling us the x dt is c1 cosine 2t plus 2 sine t plus c2 times minus 2 cosine t plus sine 2t plus 1/3 sine t minus 3 cosine t.
Makes more sense.
Come on. But that's what it's telling us mathematically. Let's look at the let's look at the phase portrait of just our system. I'm not certain. I'll try afterwards, but just this system, and then I'll try to see if we can do a phase portrait for non-homogeneous. I haven't tried yet, but we'll see.
That'd be very cool. It's just gonna wiggle around for.
I think we might be surprised.
Yeah, you never quite know what's gonna happen. It's just gonna like. All I know is that there's gonna be a lot of super. I feel like it's gonna be like a surprise movie. You know? Maybe it gets like bigger and bigger or something. Is there any like twos or? Wait, no, that's still one big hit.
And what we're looking at here is related to that problem 51 and 56 that were linked in last night's homework. So our original, without the sine and cosine driving term, we get, what was our original system?
This homework got a lot of trees.
-1, negative x plus 5y. Oops. Negative x plus y. I just have them in different order. -4 to 4. So this is just the homogeneous system.
Interesting. It's like repelling it from somewhere that's like curving towards the middle. It's like curving away from the real line. Looks like there's almost like a x and y axis on it.
So let's think, what are these shapes?
Oh, that's 1/x.
Now those are hyperbolas. And did I type this in right? Yeah. Now let me go back and see, can we put a non-homogeneous term here? Is this minus 2 cosine t?
Yeah. It's gonna freak out.
Oh, yeah. Didn't like that. So let me search here.
I feel like they've been able to do that for a while now. Well, it's just like me playing chess when I was 5. You just smack all the pieces away and then win.
Exactly. It's just like they're like hits and on lines that they don't even have on.
That's just what I used to do when I was losing.
Let's see what this.
Ooh, I like that one. This one doesn't have the,
It's the one with the nice, like, visualizer. There's something about fluorescence that they use.
that's just a picture. It's
Yeah.
You'll learn that.
Oh, let's see. Oh, doesn't like that. Hmm.
There's gotta be somewhere where we can do it, right?
It would seem like it.
Maybe it's too hard. I think we beat the internet. We defeated the internet. I can do math better than the internet can. Well, to be fair, I bet they could solve it. They just can't phase plot it. It's not like this is what computers are supposed to be like rewarding something.
Yeah, this one just homogeneous systems.
Why aren't they all sliders? That's so weird. Why would you want to?
So yeah, the slider is adjusting the.
Yeah. You can see how it changes in real time. I guess. And you were hating on it. No, it's still like typing it in would still be better. Oh my god.
Well, imagine there's like a higher, like a t squared sine t.
Yeah.
Oh.
I will look some more for this for a non-homogeneous phase portrait plotter.
Do you know what it
That-
looks like?
I don't.
I feel like we can make a guess. That just wiggles a bunch.
So we would. So if we look at our, I think if we go back to our phase portrait, and then we add for each one, we're going to have a sign that's going to vary in time. The derivative is going to vary in time. So yeah, that's. I'm not sure. I'm not sure. But I'll look some more. So back to our system, and back to undetermined coefficients. So unfortunately, the examples that we did make the process seem more straightforward actually than it is.
Really?
Because if our function f of t contains one or more of the functions that are in the complementary solution, the rules for how we have to form our guess for the particular solution are more complicated than for higher order differential equations. So it's not just a matter of adding a t or adding a t squared. You actually, for many of them, you usually have to add additional terms with vector coefficients in addition to those t's and t squareds and that kind of thing. So the rules get a lot more complicated. So rather than going into all of those rules, if it gets to that, then we would choose to use undetermined coefficients. Or sorry, not undetermined coefficients, variation of parameters, which is what we'll talk about on Tuesday. And the difficulty with variation of parameters, from what we saw before, is usually one that involves evaluating integrals, which is just a never-ending struggle, evaluating integrals. But yeah, the variation of parameters, the method is a little more, it always works. It's a little more straightforward. It involves some matrices and derivatives, or not matrices, inverses, and then integrals. And of course, we're integrating matrices, so column vectors. So we have to evaluate multiple integrals for each of our functions. So the examples that we'll do for undetermined coefficients tend to be more straightforward.